Ladies and gentlemen, what a wonderful good morning. Hello and welcome to this video on sentence embedding. Our topic today is gonna be the local connectivity of your data that you want to embed in. And the last videos I showed you a lot about the dimensionality reduction and the clustering algorithms. We focused primarily on UMAP. And today I'm going to show you a particularity of UMAP if you want to conserve your local connectivity of your data on the manifold in a strong way. There's a beautiful algorithm that's already integrated in UMAP, and it's called densMAP. So here we go. Let's start. As always, this is real-time coding. So we run here our JupyterLab. In real time, we have either installed the transformers from HuggingFace. We have here the proceedings where the publication from SimCSE has been done by Rimus. And I showed you the pre-trained models already, the textual similarity. All this is familiar with you. We have done this in the last videos. And today we directly load our trained model from Colab. I have here already all our, I think it's about 4,000 sentences. Yes, it's about 3,916 sentences. Those sentences have been learned, have been now designed to be embedded in a 768-dimensional feature space. Our sentences are sentences for more than 35,000 European research projects, where I focused on water and biodiversity. And you see here, from those about 4,000 sentences, this is a typical sentence you would get. Already showed you everything about knowledge extraction, and today we are going to jump into UMAP. Now, just short reminder, the assumption of UMAP and why UMAP is working so beautifully in the dimensionality reduction and then the clustering algorithms, that the data is uniformly distributed on some manifold, and that is ultimately this manifold that we would like to present. So you see uniformly distributed on some manifold. Well. The methodology behind UMAP is beautiful. You should read it. In short, it is simplicial complexes that are a means to construct topological spaces out of simple combinatorial components. You can reduce the complexity. Reduce the complexity. And you have some relative simple task of combinatorics and counting. Simple, okay. And now there's an advanced version, if you want, densMAP. And densMAP computes the estimate of the local density of your data. And those estimates are, if you want, a regularizer in the optimization of the low-dimensional representation. So you say, I have a very strong focus on a local density, and I want that this local density is also presented in the low-dimensional representation, even stronger that it is already done in UMAP, and this is the beauty of densMAP. But densMAP has some interesting features, and I will show you in a second. So we have our embeddings of our 4,000 sentences, and the length of our sentences, just to check, 3,960, dimensionality 768, and also here 3,916 sentences. Now, if you want to learn about both, there's a beautiful presentation of UMAP, and you have here better preserving local density with densMAP. So it is now part of UMAP. Have a look at the code. You can learn quite a lot of it. I also found it very interesting to read the original paper from the densMAP team. Density preserving data visualization unveils some dynamic patterns of single-cell transcriptomic variability. You can download the PDF and have a look at all the methodology. In short, you have a high-dimensional data set in, I don't know, 1,000 dimensions. Then you have a manifold approximation, where your focus is on nearest neighbors. And then you do an embedding, and you hope that the new dimensionality reduced embedding conserves the structure, the topological structure of the manifold. Now here, in addition, you have now the conservation law, if you want, of a local radius, a density estimation of the locality, and you preserve not only the nearest neighbor structure, but also the local radius. And this is the density augmented embedding, and this is what we called, well, the author calls densMAP. Highly interesting now from the publication of densMAP, just to understand what is here the particular topic. Let me show you the original data. We have here 6-point clouds, a data set of 6-point clouds. And you see you have here the yellow is the smallest in the size, in the diameter, and then it grows, it grows, it grows, the variance increases. Now here, if you transform these 6 data sets in UMAP, you get very clearly structured 6 data points in the reduced dimensionality of a topological of a vector. Now it's a vector space. And with densMAP, now if you want to preserve the local density, the local function, you see that here yellow is also the smallest dot, the smallest radius. And here, I don't know, let's call it violet, blue, violet. We have blue and violet, and you see here that the local density is significantly different as it is in the original data compared to UMAP, where more or less all the data have the same, all the dots have the same diameter if you want. You can have now some data sets where you have the same variance, the spread out, but the number of the sampling rates, the number of the dots per data set is different. And you see here, I would argue that green and yellow have the highest sampling rates within the set. With UMAP, you see that you already start now to see, yes, these two here already have a significant diameter. But if you take densMAP, you notice that the distribution, now independent of the sampling rate, looks, in my eyes, much more similar. You see here the locality here and the locality here is very much preserved, and you see that it is not just here simple dots like in UMAP and then it spreads out a little bit, but here the locality is beautifully reserved in densMAP. But to tell you, densMAP is not a simple algorithm. And to show you the beauty, let's have a look at this dataset C. The original data is, let's say you have an explosion at the point in the middle of this yellow dataset. And then you have here a translational motion, and of course time is passing. So the way the particle moves, the debris of the explosion distribute. And you have here a cloud of debris here already. And if you have a look, and if you transform this in a high dimensional, from a high dimensional space to a low dimensional space with UMAP, you see here at yellow, let's say at the start of the explosion, you have the same, I don't know what to call it, diameter here. Then it's, if we run backwards now in time, if here now at the end where we have a highly distribution fragments of the explosion, and it is more or less the same structure, the same topological structure in this low dimensional representation. And densMAP, and I suppose this was the reason why it was also included in UMAP, now gives you a much better idea. Okay, yellow, the point of explosion, the debris start to fly apart. Then if you have a velocity, also time passes, and then you have a cloud of debris here all over the place. So it gives you a much better, and I think a much more similar representation in this low dimensional space compared to the original data in the high dimensional space. So densMAP, wow, what a step in the dimensionality reduction and clustering of data. Now in our example, each dot is a sentence. And I have 4,000 dots, I have 4,000 sentences, all about a research topic about water or biodiversity in a European ongoing research projects. And I have now a look at this. densMAP has more or less 5 parameters. At first, you have to put the flag of densMAP to true. You have a lambda parameter. It is normally, as default, is set to 2. And larger values of dense lambda make preserving the local density a priority over the normal UMAP. You have a density fraction. That's the fraction of epochs. You have a variation shift. It's a numerical, a minimal numerical value. And you can also have then an output of the local RADI for the embedding, but we don't need this in our case, so we set it to false, as it is by default. So this is now our UMAP algorithm. We have the number of neighbors, we have the number of components. So I have, say here, a local neighborhood I want to have connected is about 12 dots, 12 sentences. And the dimensionality of the space I want embedded is I want to embed the high dimensional space of 768 dimension to a 12-dimensional space here. And then, you know, you're familiar with UMAP. You put in all the different parameters and you run it, and you see here I have my densMAP is true and lambda and dot 4 is commented out. So if I run it, just to get a comparison between the pure UMAP and the densMAP version of UMAP, and where some problems may arise if you're not careful with the distribution of the dataset or this manifold that you want to embed in. So it takes a little bit of time because I have a learning rate from 1.0 and I have the number of epochs is 5,000. And I've performed this operation here on my local PC where I have no GPU acceleration, but you can see we're almost done with our 5,000 epochs. And here we are, 36.7 seconds. Now, just to make sure, short check, we still have 3,916 sentences, and now we have an embedding of each data point in a 12-dimensional feature space. I also like to check some numerical values. So this is the first 3 dots, if you want, of a data set. Here is a 12-dimensional representation, 12-dimensional feature space, if you want. And just to make sure, I have 2, 8, 7, 1, so I have a widespread. You want to ask, hey, Thomas, what are you doing? Because here there's a minimal distance also, the effective minimum distance between embedded points. And if you have, for example, everything close to 0, you should be careful with some numerical value adaptation. And I like to check always where am I and how evenly spread is all my data set. And now the clustering algorithm. We do the cluster algorithm in my preferred value. I have a minimum cluster size of 50 and a minimum sample size of 20. The higher those values here of the minimum sample size, the more conservative the algorithm will be. This means the more the identified cluster will be restricted to the more dense area of the cluster, and the, let's say, peripheric clustering will not be regarded as part of the cluster. I have here an L2 and a Euclidean metric. I have an epsilon defined. My methodology is not EOFs and leave, and I just let the system choose the best fit. I have my 12-dimensional embeddings I start with, and I want to cluster them. And as you can see, I have my 3,916 sentences, and the number of clusters 12. Now, interesting here, cluster, since the cluster algorithm also regards noise, and not every dot will be assigned to a specific cluster, there's this beautiful cluster of -1. -1 means this is noise and not specifically allocated to one of the operational clusters here below. This is the number of sentences per cluster. So from, let's say, 4,000 sentences, more than 2,000 sentences are regarded as noise here in my system. So this means you lose half of your data, which are not clearly assigned to a specific cluster. Now you might say, okay, how does it change if I change the parameters? So let's say we activate now densMAP, and we take the default parameters. We let it run another time for about half a minute. Of course, we will get the same shape. We will get now, let's have a look at it, a different numerical value distribution within the tensor. I'll let it run again for 5,000 epochs. I didn't change anything. in my standard parameter. My spread is still 3, and my local connectivity is 2. Learning rate is 1, number of epochs is 5,000, and here we go. Yeah, we can have a look at the shape. It should be, of course, the same. So the shape we expect, 3,916 to 768 to 12. Stop. Since I have a dimensionality reduction, 12 dimension now. And here we see this 12th dimension. We see that the numerical spread is 4, 9, 7, 8, 2. Yes, beautiful. So yes, we are not somewhere agglomeration at a point, I don't know, 22058, but we have a nice spread out. So now if I change nothing at my cluster algorithm, and just to remind you, we have here operational cluster 12, and 2,170 sentences are not assigned to an operational cluster regarded as noise. If we run now with this, we see now a significant change in the number of clusters, but we also see that now almost from our 4,000 sentences, 3,000 sentences are regarded as noise and not counted and not assigned to a cluster. So suddenly I lose 3/4 of my data because now, and going back here to this distribution, if you imagine I have here, I don't know, let's say 100 clusters, and each cluster is about spread out like this, and those clusters are really close together, and suddenly I do not get such a clear structured UMAP dimensionality reduction, but I get this, let's call it washed out, this smeared out here distribution, and I have another 100 cluster of this distribution here in this box. You see it's completely filled with dots. So there is no clear, let's say, distance, whatever Euclidean distance or whatever Manhattan distance you want to apply, Minkowski metric, between the dots to be separated as clusters. If everything from the local connectivity, if you want, is spread out, it becomes just like a Brownian motion of a gas in a I don't know, in a glass. So be careful if you have a lot of clusters and you have a lot of, let's say, starting elements in your high dimensional topological space here, constructed space here, they will smear out completely, and the cluster algorithms will have a hard time. And the result, as you can see now here, and the clustering is that 3,000 sentences are regarded as noise because the algorithm does not know how to assign it to an operational cluster. So this is a critical element. Now, of course, you say, hey, Thomas, we have here the lambda function, we have here the fraction, we can play around a little bit. And of course, you're right. If, for example, 2 is the default value for density lambda, if I'm now crazy, UMAP would be 0, and I put it to 10, and I say the density fraction is now 0.9, and I let the embedding run here that we create a 12-dimensional reduction embedding. And I say I run here the test again. How will it change if I change the parameter of densMAP? It will change. It will change significantly, as you will see in a second. In about 30 seconds. Come on. Yeah, of course, you could, by the way, reduce the minimum sample size. Normally, sometimes I choose to put it to 2 so that it is really a progressive cluster algorithm. And I try to catch as many data points close to a cluster that belongs then to a cluster. If you have, for example, 20, which is already a significant part of 50, the minimal cluster size, you are more conservative and you have a higher amount of noise. So now with the density lambda to 10, you see that you lose more than 3,000 sentences. So now you have about less than 900 sentences in your dataset left. The amount of clusters are further reduced to 7. So the sharper or the more important you put your focus on the local density here, the more spread out all the dimensionality reduced embedding will be, and the algorithm here, HTTP scan, trying to sort out the cluster in this mess has a much harder time, and you see the number of sentences not being assigned to an operative cluster is extremely high. 3/4 of our data set we lose. So be careful. If your original data, my data are sentences. So if you have some other numerical data, I don't know what you're looking at, that have a clear density function, a clear local focus on densities, and are much clearer separated, because my sentence embedding, the sentences are not clearly separated. I mean, yes, you have maybe a topic about physics, a topic about mathematics, a topic about, I don't know, computer science, but more or less based on the training data, it's all, well, let's say, meta cluster science, and then you have subclusters. But if you have your data that are clearly separated, that clearly belong to a different genre, a different, I don't know, data pool, the separation function, even on a local level, would be much better, and you would get much better results. So this is just to show you, if you operate with UMAP and you switch to densMAP to increase, if you want, the local density, and where you have this local density function as a regularizar in the optimization of the low dimensional representation. It's a beautiful algorithm, but be aware with the complexities you approach, and it all depends on your data distribution in a high-dimensional data space, how clearly they are separated, and how you go on with your calculation. This was it for today. I hope you enjoyed it, and I will see you in the next one. Thank you, and bye-bye.